ask some thought-provoking questions and give him a challenge.
My question is, if a curved line has infinite points, then why it has finite length?
Okay. If a line has infinite points, why does it have finite length? Or
If a line has infinite points, then why does it have finite length?
all right. Well, the problem is a point itself isn't defined to have any length. So, okay, look. When we go from a point to a continuous function like a line, when we're measuring the length, we're not thinking in terms of a point. A point has an infinitesimal, well, it has zero length. We can't really say that, and when we work with like infinity, infinity is simply just notation. So it's mainly used for the limit as x approaches infinity, limit as x approaches negative infinity. And these are ways to not break notation, but what they really mean are x is increasing and x is decreasing. So using infinity as an actual number in operations becomes very paradoxical because how big exactly is it? So I don't really know what to say. I mean, we can debate about how I guess the cardinality of the set of points that a graph holds, which would probably be equivalent to the real numbers. But all I can say is the length of a line does not depend on the amount of points, of course. Length of a line simply depends on the length of the axes that we need to use to describe it. So, I mean, if we've got a straight line right over here, then all we need to do is use the axes to describe it. If we have 3 over here, 4 over here, this is obviously 5. But this contains no mention of points. Points, I mean, don't really contribute anything to the concept because if they do, then let's say we have this right over here, these points right over here, and these points right over here. These all have infinite length, but somehow these all have infinite points, but somehow they all have different lengths. So that's just what happens when you try to consider length in terms of points, which don't have any length. Points and length are not inherently related concepts. So I know it's not a very satisfying answer, but essentially, we can't talk about the length of something in terms of the points that compose it. That would be like talking about the area of a square in terms of the lines that make it up. It just makes no sense because each of the individual lines has zero length. And of course, you can change the dimensions and it's still going to be infinite lines, but there's going to be a different area. So it doesn't really make any sense to talk about a length in terms of points or area in terms of lines or volume in terms of cross sections. So that's just my personal opinion, but I don't think we can really justify using it that way. Thank you.
So, few questions. Yeah. Could you please? Hello, my name is Rafa Zarin. So my question is, can you give us the concept of Ramanujan Hardy number and why this number is so special?
Uh, I don't exactly remember what a Ramanujan Hardy number is. Let me think. Uh, no, I can't remember. Uh, Taxi? No, it's not. It's not a taxi cab number. I think. Uh, no, I can't remember what a Hardy Ramanujan number is. Does
It's 1729.
oh the taxi cab numbers? Oh, uh, the taxi cab numbers have no real application. They're just some very nice things that Ramanujan once observed. They're just noted because it was how Hardy demonstrated Ramanujan's uh, innate sense of detail and astuteness. So essentially, a taxi cab number It's just a fancy word to describe any number that can be written as the sum of two different cubes. So, like for example, 1729 can be written as 1 cubed plus 12 cubed. And if I remember correctly, it can also be written as 9 cubed plus 10 cubed. So that's what makes it a taxi cab number. And of course, there are a lot more of these. I believe we've discovered around 16 so far, but they get rapidly bigger. And we haven't found any real use for them besides perhaps cryptography, because I mean, cryptographers always enjoy having a new way to encode their systems using extremely long numbers. So a taxi cab number has no real application. It's just Hardy's comments on how Ramanujan was very noticeable of detail.
Thank you.
Thank you.
So we are here not only learn, we are also here for the sharing of knowledge so that you can also get the good memory with you. So any next question? Next question, please. Oh, C rates. So just come forward. Your name?
My name is Monirul Islam. A very good evening. So when we add the multiple of 9, the result comes 9. For example, 9 into 2 18. 8 plus 1 is 9. 9 into 3 is 27. 7 plus 3 is 9. And why?
Oh, this is the exact same question that was asked at the other session. I'm sure if any of you showed up to that one, you would have remembered it. But essentially, it's just modular arithmetic. So basically, if something is congruent to another thing, mod 9, so let's say A is congruent to B mod 9. All that means is that A can be written as B plus 9 times K, where K is some integer. So, for example, 12 is congruent to 3 mod 9 because 12 minus 9 is 3. And 12 is also congruent to 21 mod 9 because 12 plus 9 is 21. So, as you can see from this, you can probably infer that if something is congruent to 0 mod 9, then that means that it's going to be divisible by 9. And you can also add these modulo. So, if 12 is congruent to 21 mod 9, and 5 is congruent to 14 mod 9, you can guess 12 plus 5 is 17, 21 plus 14 is 35, 17 is congruent to 35 mod 9, which turns out to be correct because 17 is just 17 plus 18 gives us 35, and 18 is, of course, a multiple of 9. So here's what happens here. What's going to happen is if we have a multiple of 9, let's say we have 10 to the n times our first digit, d1, plus 10 to the n minus 1 times our second digit, d2, plus 10 to the n minus 2 times our third digit, d3, of course. And this is just basic place value. So we've got n digits just like this. So this is just going to look like d1, d2, d3, all the way to dn, n digits. So then, here's what's going to happen. This has to be congruent to 0 mod 9 because as given in the question, the number has to be divisible by 9. And now we want to show that the sum of the numbers is also going to be divisible by 9. So we want to show this. And of course, this is actually quite simple. Oh gosh, this is a strange eraser. Okay, so this is very simple because think about what 10 to the n is. 10 to the n is just 1 followed by n zeros. And so we can rewrite that as 99 dot 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 99 with n minus 1 digits and then adding 1 to the end. And so, of course, this is a multiple of 9, so it's congruent to 0 mod 9. And this is just 1, so it's congruent to 1 mod 9. So that means this in total is going to be congruent to 1. So then what we can do is say 10 to the n d1 plus 10 to the n minus 1 d2 plus dot 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 plus dn. This is going to just be congruent to 1 times d1 plus 1 times d2 plus 1 times d3 plus dot 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 plus dn. And of course, we already know at the beginning this is congruent to 0. And so that means this must also be congruent to 0, which essentially means that the sum of the numbers have to be a multiple of 9. So long story short, it's because the place value that we use, or the number system we use, base 10, has the very special coincidence that 10 is exactly 9 plus 1, meaning that any multiple of 9 will have the sum of its digits is 9. The same exact thing works for 3, because if you subtract 3 from 10 3 times, you'll get 1 again. 10 is congruent to 1 mod 3, which means that any multiple of 3's digits also sum to a multiple of 3. So that's essentially a modular arithmetic reason for why the sum of the digits of a multiple of 9 is always also a multiple of 9. And of course, it's not always exactly 9. It can be 18 or 27. 999 is a multiple of 9, and it sums to 27 with its digits. So it's a very interesting question, and thank you for asking it.
Okay. You want to, can you please come forward?
Sir, can you make it like this, one by one dot?
That way, yeah. I will take that. So please, can you please, those who raise hands, please come forward so that I can also identify. Okay, please come sit and take this sofa set. Yeah, please. So now one girl has been suggested by Professor Marisa. One girl and one.
Good evening, Professor, and to all the people present out here. I am Farida Tanvi. I am from MI's Girls Campus. I study in Standard 10, and I have wondered about something.
Are you kidding me? Okay, sorry.
My question to Professor is, why should we search the space? What is the justification that we spend a lot of effort and money to go out there and search the universe? I feel and I believe that there are better causes here on Earth.
Oh, sorry, what was the last part?
I believe that there are better causes to study the Earth than to go out in space and research and search about the universe.
Yes, the truth is, unfortunately, uh, exploring the rest of Earth that we haven't already explored, such as exploring the deep ocean, which is essentially the only place that we haven't explored. Exploring that place, unfortunately, takes more money than actually sending out the probes that we have to all of these missions out there. The truth is, even though we've been sending these unmanned probes, it's been 60 to 70 years since anybody has sent any manned mission out there to the moon. So actually, what we're looking for is not only a reason to be there again, but also some sort of way we can obtain resources, because it turns out that the resources and minerals you can find on many of these asteroids and other planets are much more valuable, are very valuable compared to the minerals that we can find here on Earth. And they can also potentially remain as supplies in case we run out of what we have here on Earth. Meanwhile, the deep ocean, although it's already hard to explore, doesn't have many foreseen benefits. There are maybe a few new species discovered, for example, but it's already unfeasible to build, for example, housing that's close to the surface because it's extremely expensive. So building houses and other equipment down there would not only be extremely expensive, but also nearly impossible because of the actual pressure. So it turns out it's just a very expensive endeavor, and outer space has better options than what we have left to explore on Earth right now. Thank you.
Tokyo, one single question.
Come over here. Come over.
What?
Actually, a little bit long question. Can you know this?
Oh, this is a funny one. Yeah, I've seen this before. So, what should be the value of L such that the goat can only eat half of the field's grass? So, essentially, what's happening here is we've got a square of side length A, and a goat is tied to the midpoint, and essentially we have a rope of length L to which the goat is tied, a leash, and we want to find the length of the leash such that it can't eat more than half of the grass. So we're going to draw a circular arc around here. So I think this is good enough. So essentially, we want to make sure the sum of this circular arc, as well as these two halves, only sum to half of A squared, half of the field's area. So, of course, this shouldn't be too hard to do. All that has to happen is we have to take A and draw our leash again, and we're going to extend it out both ways and draw the respective circular arcs. So first of all, I kind of want to find this theta in specific. So how do we find that? Well, it should be pretty simple because actually we're not going to find this. We're going to find this theta because we already know the length of this. This is A over 2, adjacent over hypotenuse, so A over 2L. So we know theta should be arc cosine of A over 2L. All right, so then we have that this is just going to be 90 minus this. So
हमारा भारत तुम्हारा भारत प्यारा भारत